this here? I don't know.
We won't enter.
We stand here. Sorry, we're not allowed.
Yeah, well, they're not entering.
They're not entering. And standing here.
We have to keep the door shut.
So a nice example of an optimization problem, the hard problem is scheduling courses and conferences like this to rooms, periods. And just to get you an idea of what kind of problems the hard and complete problems are, give a quick demo. And due to the problems here, maybe I can show the course Annealing problem. So the idea is you have to assign a number of lectures or conference things to rooms which are on the top and to periods, and you have to make sure that the teachers here, in this case it's courses of course, that all the teachers can actually go to all of their courses that they have to teach, and all the students, so basically these are curriculum groups, that they can also go to all the courses. So in this case they can, for example, if I would move this lecture to one up, you'll actually see that they can't. And then of course you get some hard constraints broken because it's no longer feasible. Now, what are meta-heuristics and heuristics and so forth? They will actually improve the solution. So as you can see on the bottom, there's a score there, and this is how unhappy students are with the schedule. And if we apply some meta-heuristics on this, you can actually see that students get happier and happier. They will never be perfectly happy, we will never reach score 0. It's basically impossible, but as we give it more and more time, we do get some improvements, and we get to something like 51 if I recall correctly. Okay. So this is just one example, there are many others. Employee rostering, so making sure that people can go to that early shift and late shift and support what filled in at the company. Another nice one is vehicle routing, where you have to basically decide how your vehicles or your trucks will drive through the country and drop stuff off. And you have a couple of hard constraints here that the capacity of a vehicle is limited, so you can only put in a number of items. You can see how many items you have to drop off there. And of course, sometimes you actually have harder cases where you actually also have to take into account timing when they arrive and so forth. And you can actually have many constraints. And all of these constraints, many of them fight against each other, right? So now, because of these problems are NP hard and NP complete, they are pretty hard to solve. And you need a lot of computation power, and they scale horribly. And I'll get back to that during the presentation. Now, while I'm explaining the algorithms, I'm actually going to use the NP's example, which is not NP complete, which is not NP hard, so it's a little bit of a bad example. I'm going to use it anyway because it's the easiest way to explain you the algorithms, what they do. So in the n-queens problem, it's quite simple. Place a number of queens on the chessboard, 8 queens on the chessboard, and make sure none of the queens can attack each other. You can see none of the queens can attack each other, that's what we want, right? So a 4 queens problem is simpler. There's 4 queens on the chessboard that can attack each other. This is one of the 2 solutions. This is where we want to get to with our algorithms. So, okay. Let's take a look at how we can get there. So, like I said before, no 2 queens can attack each other. So this is bad because A and B can attack each other and C and D can attack each other. This is good. This is where we want to get to. Yes, like I said before, it's an imperfect example. So which solution is better if you have a number of solutions here? Well, you can easily see there's no optimal solution where none of the queens can attack each other. But you can also see that this one over here is probably very bad because all the queens can attack each other. So this is definitely something we don't want. The others might be better, so we need to somehow figure it out. So we need an objective scoring, and a better score means better solution. And we want to find the one with the highest score, because that's our optimal solution, right? So there are many ways you can define your constraints and so forth, but for n-queens it's very simple. Every time a pair of queens can attack each other, we're going to reduce the score by -1. So here we have -2 because A and B can attack each other, and also B and D can attack each other. So that's 2 times -1. In more complex cases, you have weightings, of the scores. You have actually levels where some constraints are infinitely more important than others. You might actually more than 2 or 3, 4 levels. And you can even have more complex constraints like variables. But anyway, if we go back to our 8 solutions we just generated a minute ago, you can see that now we have an objective where you're saying this is really bad, -6. We have also seen that this is pretty good, it's -1. Now for n queens it's simple, we know the perfect score, it's 0. But if we do something like vehicle routing or like course scheduling, we don't know the perfect score in advance. So this might actually be the best thing we can find. Now the question is, how do we write an algorithm which finds us the solution, right? We need optimization algorithms and we need the best solution in available time. So one way to do this is with exact methods, right? So brute force, basically try every single combination. So here's an idea what will happen in that case. We start off with an empty chessboard on the top, as you can see. So every queen is bound to its column. We will not try putting 2 queens on the same column. So for example, on the top row, so there we're putting queen A, which is the first column. On the first row, then on the second row, then on the third row, and on the fourth row. So that's the first thing we try. But the problem is that from there on we branch out further, because we're basically going to try every combination, but now that we've placed queen A on the first row there, we're going to try every combination where queen A is on the first row, below that. And then when we place queen B on the second row and queen C on the third row, each time we're going to try every combination below that, which is still possible. So if all 3 queens are on the same row, we're going to try all these combinations, all these 4. We'll see, of course, that all of them are the best score we can get is -4, and then we will basically try the next one, and next one, and next one. At some point, we will try this combination. We'll find a feasible and even an optimal score. But if we don't know the perfect score, we'll actually continue until we get to all of them, and then we'll figure out, okay, these are the optimal score, and might actually find them. We'll actually import them. This will take 264 steps for queens, but the optimal one we have to find it at about half, right? Now, the thing is, how does this scale? That's where it goes bad. So 8 queens takes 8 seconds, 9 queens 3 minutes, 10 queens 1/3 an hour, 11 queens a day, 12 queens a month, 13 queens a year, and we want to get to 100, 1,000. 10,000 queens, 50,000 queens, we want to get to there. So basically there's this wall coming at you, and brute force doesn't work, that's pretty simple. Right? So quick idea, 100 queens, how many combinations you have there? Well, it's 100 to the power 100. So that's 10 to the power 200, so that's a very big number. That's the number of combinations you have there. Right? So more generally, it's the number of values times the number of variable sets. So if you have, for example, lectures, you have, let's say, 5,000 lectures, and you have 40 rooms, that's 40 to the power 5,000, which is very big. Now, when you try, let's say you have a very, very fast computer where you can do about 1,000,000 of these evaluations of the score, and you remember for each of these evaluations of the score you need to compare if any queen cannot detect any other queen. There are some performance things you can do there, but basically you do need to do that. And let's say we can do about 1 billion of those per millisecond, then we can do about 10 to the power 20 scores per year. And if you then see how long this would take, let's say 400 queens, that would take 10 to the power 80 years. For 10,000 queens, that number is huge. The thing you have to realize is that Moore's law is a drop in the ocean here. You cannot solve this by throwing more hardware at it. You cannot solve this by waiting until Moore's law doubles your CPU power or your number of cores with Annealing's law and so forth. That doesn't work. It shaves, even if it's on 100 queens, you get to 10 to the power 178. That's the same number, right? For us, it's too long. So of course, many of you already saw why would you put 2 queens on the same row here? That's a stupid idea. Don't do that. So the next improvement you can do on top of that is that first search with backtracking. So what you do is you go into the most promising branches first. Now on the top you really don't know. You've put the four queens there. You have 4 options there. So let's just take the first one. And then when you start putting the second queen, you immediately notice, okay, this is a bad idea because I have more promising branches now. This one looks promising. So you investigate that. Then you come to the conclusion that there is no feasible solution there, and we have promising branches which currently still have a better score. So you backtrack from these up, and you go and you investigate this one further. Also, again, no feasible solution. You still have more promising branches over there, and you backtrack, and then you get there. And it's apparently 26 steps here. The problem is that this scales badly. Again, it doesn't break down at 10 queens. It breaks down at 20, 30 queens. It doesn't scale again. There are a couple of tricks there again which you can do, but more generally, branch and these kind of backtracking and so forth, once you get to serious numbers, serious scale, they don't have enough CPU power, they don't have enough memory. Because why don't you have enough memory? It's because you have to remember all your promising branches. And now we're only showing 4, but if you have 8 queens, then you have 8 branches of every level. If you have 100 queens, well, you can have a lot of promising branches. So, how do you solve this? Well, one thing you can do is go for construction heuristics, where you basically just say, I'm going to place the first queen where I'm going to take a queen, place it, take a queen, place it, take a queen, place it. So it's basically first come, first serve. So here, as you can see, a number of people are wanting a room, right? And you give the first person a room, you give the second person a room, the best available room, and then the third person the best still available room. So if we do that with queens, it's the same thing. We take the first queen, we place it in the best available remaining spots. Well, it doesn't really matter, so we take the first one. But then for the second queen, well, we won't place it here and here, we'll take this one. So it's kind of like the backtracking thing, but the only difference is that you don't backtrack. You just go down, and at some point you come to the solution where all the queens have been placed. That's a construction heuristic. This is what you get. Of course, this one isn't feasible. It has a score of -2. But it does give you an answer in reasonable time. You don't have to wait 10 to the power of 180 years, which is nice. First set decreasing is an improvement upon that. What you're basically going to do is you're going to say, okay, we want to place the queens which are more difficult to place. So in course scheduling, the courses which are more difficult to place, we're going to place them first, which are more likely to hinder the constraints and so forth. So we're going to order them. So in this case, you're going to order the person which you want to give priority to first. And so if you do that for n queens, we're going to place the middle queens first. Why? The middle queens are the most most difficult queens, because if a queen is in the middle of a chessboard, she can attack far more than she's in the corner. So if you ever play chess, keep your queen out of the corners. Now the point is, if we do it like that, and we follow basically the same algorithm again as we did 2 slides ago, we now get to -1, which is better than -2. Right? It's an improvement. It's a nice improvement. So what are meta-heuristics? Well, meta-heuristics will basically take this solution, which we found by construction heuristics, and will transform it into a better and better and better solution. And there are a couple of ways of doing that. So, so basically we take an empty chessboard, we add the construction heuristics, and then we do meta-heuristics such as Tabu Search, which is one of the meta-heuristics to get to our optimal solution, right? So, okay. How do you get to a different solution? Well, you basically do a change. There are many different ways of doing a change, but the most simple way of doing a change is take one queen and move it to another position. So if you're in course scheduling, you take one lecture and you move to another room, or you move to another room at another period, and so on. Now, the thing to understand is that the number of change moves is actually far less than the number of solutions. So it's n to the power 2, while the number of solutions is n to the power n. And even in that case, we're not going to look at every possible move. We're going to look at a subset of those, because even if we go to like 1,000 moves, and well, looking at a million moves is getting hard actually, in some cases, depending of course on any constraints there are. Now the thing is with actually sequentially doing moves, you can actually get to any solution which is possible. So you can, like you can see here, we start from the solution where all the queens can attack each other, and in 3 moves we're actually already we can actually get to a very, very different solution. So what's the first algorithm to pick these moves? Which moves do we want to do? Well, the first algorithm is hill climbing, where you basically just say, I'm going to look at all the moves, which you can see. So I start with the solution. This is a very bad one. This is not done by construction heuristic, but by not even randomly. It's worse. Just put them all on the first row on top, as you can see there. But we're going to look at all the possible moves. We're going to try every possible change move on that. So that basically means we're going to move 1 queen in every solution we look at, and then we're going to take the one with the lowest score there, and on that we're going to do again the best move which is possible on that. So after a couple of steps, you actually get to the optimal solution. Now there's one big problem with hill climbing, and it's the reason why it's not called mountain climbing, is that once you get stuck in an optimal, in a local optimum, so where any move you do actually degrades your score, but it's not the optimal solution. Like here, you always go up, but if you don't look far enough, if you're not seeing the other mountain, you're going to always be stuck on this hill. You're never going to cross the chasm to go up the mountain. So that's why, for example, here, local optima hill climbing can get stuck. It might start chasing its tail. So it's actually quite a bad algorithm. But yeah, if you start with the construction heuristic and then with this, at least you have a solution, and at least it's better. The improvement upon that is Tabu Search, which is quite simple. You remember wherever you've been, and you don't go back there again. So, so for example here, he's been to Mount Lofty, which is like the 2nd biggest mountain in the world. So he'll try a different path, which is actually going down, which you never know. At least it's going down compared to this path. And you get somewhere else. So with Tabu Search, what you get is that he starts out the same as hill climbing, he tries every move and he takes the best one. But what he then does is he remembers, okay, I've just moved, let's say, queen B, and he remembers, okay, I've moved queen B, so I'm not going to move that now for a number of steps. In this case, it's 2 steps. And then he will be forced to move any of the other queens. And this is actually the case where he got stuck chasing its own tail in hill climbing, and he actually gets out of that because he is unable to move queen B. He moves one of the others. In this case, he moves queen D, and the result of which he gets to this solution, and the next solution is actually optimal. So the slide wasn't big enough. I'm running out of time. Another one is simulated annealing. This works pretty much like, what is annealing? You take an iron bar, you take steel, you melt it up, and you slowly cool it down so that the molecules can sit next to each other. It's the same thing, it's simulated here. What you do is, you start with a solution, you generate a move, and you're going to accept this move if it is better, or when it is worse, you're going to accept it with a certain chance. So if, depending on how much worse it is, and depending on how much time you've already been solving. If you're near the start of your solving schedule, you're going to pretty much accept any move. If you're near the end, you're pretty much going to only accept moves which are improving. And this gets the effect of the simulated annealing of the steel, where the molecules fit each other. You're slowly going to converge to the optimal solution. And this seems weird, but it actually works really well. So, and every time you need to make a decision, you're basically going to roll random dice, apply the formula, which is e to the power of the diff of the score divided by the temperature. It's a nice algorithm. Big problem with this is the temperature. You need to set in a temperature at the beginning, and it's very hard to tweak that. And so it's not my favorite one because it's hard to tweak that. A better version of this is late acceptance, which is pretty new. It's invented 2 or 3 years ago, if I recall correctly. Where we're basically going to you're basically going to look at, okay, I'm going to take any score where which is at least the score of a number of steps ago. So more in long term, the score will actually improve, but in short term, we might actually go down. So something like this, we do okay. If we have a certain score at the top, -4, you can see, starting from this step, we're going to say we're going to not accept this step because the score is not approved. Okay, I'll skip the benchmarking. We have a whole benchmarking framework in Optoplanner, but if you want more information about it, ask me after this talk or so thanks for listening. If there are any questions.
Thank you, Geoffrey. Let's take time for one question.
Right. In your planner at the beginning, you were showing hard constraint and soft constraint. Here you all considering soft constraint, of course, you can use completely. So how do you do the hard constraint? How does the planner deal with hard constraint?
Okay, yeah, so you can model your score in Optoplanner with hard constraints and soft constraints. You can actually do hard, medium, and soft constraints or more levels. And it will always, it will actually go graphically compare them, which means if you have two solutions and one has more hard constraints broken than the other, the one with the least one will always win, regardless of the soft constraints. If they have the same hard constraints broken, then they will be compared on soft constraints to decide who wins. But yeah, Queens only has hard constraints or soft constraints. It only has one level of constraints, so it's
So I mean, in any case, no better would be without this. If I set only hard constraints and I want to find a solution, your algorithms maybe they're not going to find it.
Yeah, there is a probability that, first of all, you don't know if there's a feasible solution. Feasible means no hard constraints broken. And second of all, meta-heuristics always have a chance, and construction heuristics definitely that they won't find it. With exact algorithms, you have this chance, but you just have to wait a couple of 10 to the power of 100 years. So, the game is not finding the optimal solution once you start scaling out. It's finding the best solution in reasonable time, so you have something you can actually put in production. And if your company has enough resources, enough vehicle pools, that's very easy. And the game is actually to try to minimize the optimize the soft constraints, so you use as little budget and make it people as happy as possible.
Okay. Anybody else has questions for Geoffrey? Please take it outside so we can stick on schedule.